Our speaker will be introduced by Carol Covert, class of 1984. Carol serves on the San Antonio Alumni Chapter Board as the Recruitment Network Chair. Carol.
Dennis Ugolini received his undergraduate degree from Caltech and his PhD in physics from Stanford University, where he worked on particle physics with Nobel laureate Martin Pearl. He then returned to Caltech and switched fields to work on the laser interferometer, God, I got this earlier. Interferometer, the Gravitational Wave Observatory, or LIGO, which I prefer. An experiment designed to measure the curvature of space due to massive astronomical bodies. He joined Trinity University's faculty in 2003 and is currently an associate professor and chair of the Department of Physics and Astronomy. He works on improving LIGO's performance through minimizing charge buildup on the detector's mirrors. Please help me welcome Dr. Dennis Ugolini.
Great. Can you hear me? Is this close enough? All right. I want to thank Salim Sharif for inviting me back to do this. I gave the Food for Thought luncheon in 2008 where I talked about science versus pseudoscience, and at one point talked about conspiracy theories about why the towers fell on 9/11 and the mechanics of how the building materials softened and such. And I want to thank all the people who sent me months and months of email about how wrong I was. That was a wonderful experience. So something a little more grounded in regular physics research today, I'm going to talk about gravity. And I'm going to talk about the new frontier of astronomy that revolves around sensing objects by their gravitational effects rather than looking at them directly. So first I have to do a review of gravity. So you are all now having horrible flashbacks to the very boring high school physics class you took, where you learned perhaps these will be pretty much the only equations except for one other in the whole talk, so don't worry. You learned these expressions for what gravity was, and it was always an attractive force, and it always depended on, you had some amount of mass that was doing the pulling, and you had some amount of mass that was being pulled. And always, the bigger the object, the bigger the force was that was affecting it. And so you could legitimately assume, well, if I had something that had no mass at all, then there should be no force on it. So the interesting thing is, that turns out to be not quite the case. But to explain why that is, I have to make a huge digression for a moment. So believe it or not, I will tie this back to the main topic, but I'm going to talk to you for a moment about where mirages come from. So you're in the desert. It's hot, real hot. But more importantly, it's hotter down by the sands than it is higher up in the air. And it turns out that light travels faster in hot air than it does in not quite as hot air. It also turns out that light will always take the route from point A to point B that is not the shortest distance between those 2 points, but the fastest distance. So light from the sky is not going to come straight down to your eyes. Instead of doing that, it is instead going to curve down into the fast lane, ride down there for a while, and come back up to your eye at the last second. Now the other implication here is whenever light hits your eye, your brain interprets it as if it had always been traveling in the last direction it had been traveling. So if light comes up to your eye that way, you interpret it as if it had come from over here and had been traveling slightly upward the whole time. But of course, that's not where it came from. The light came from the sky. So what you see on the ground some distance in front of you is blue sky. Of course, your brain does not accept that there is sky on the ground, so you would reinterpret it as a blue thing you would expect on the ground. And you see water off in the distance. And you crawl toward it, and then there is no water, and that's where we'll leave that story. But here's why this is important here. Now we're going to go back to astronomy again. I have a super bright object back here called a quasar, and light comes out from it in all directions. In between that quasar and myself is a large galaxy. Tons of stars, tons of mass. And it turns out that that mass will exert a force, even on light, to bend the path in which it travels. So light comes off the quasar this way and bends toward me. Light comes off this way and also bends toward me. So I see light from the same object coming from different directions. But again, my brain interprets that light as if it had always been traveling in the same direction. So I see an image of that quasar up here. I also see an image of it down here. And I see multiple versions of the same object. This is called gravitational lensing. And we see this all the time. There's a galaxy, and then all four of these spots are images of the same object, which is directly behind the galaxy. But we can see the light bending in all these directions. The question I'm always thrilled when someone interrupts with at this point is, why are there only 4 spots? Who was thinking that? Be honest. All right, yay, good, you win. The reason is because this galaxy in between is not spherical. It's sort of oval shaped, and so it only has an axis of symmetry that way and that way. It's not symmetric all the way around. And so it only makes images that way and that way. If it were a sphere, you would see a whole ring of objects around it. Okay. But the important thing is what we have here is proof that gravity isn't really heavy objects reaching out and grabbing other objects. The best way to think about gravity is geometrically. Space is a big elastic sheet, like the head of a drum. Gravity is the tendency of heavy objects to warp the space around them, so that when objects go by, they follow that change in the curvature of space. So if you rolled an object along here, it wouldn't just keep traveling in a straight line. It would start looping around this heavy object like a roulette ball, or if you've ever seen those giant charity funnels in shopping malls where you drop a coin in and it goes around. If you were very small and riding on that coin, you would think you were going in a straight line. But macroscopically, straight lines are no longer straight when objects are curving space. So, geometric gravity, that's how we're going to think from here on out. Okay, the second thing we all get wrong sometimes about gravity is we have a tendency to think of it as being instantaneous. Right? If I were to drop this, which I won't because I don't want to pay for it, it would immediately drop to the ground. But that's because we're used to distances that are fairly small. When you get to enormous distances, you start to notice that gravity is not an instant effect. If, for some reason, the sun suddenly winked out of existence, we would continue to orbit it for about 8.5 minutes. And only then would the information arrive at Earth that, oh, there's no sun anymore. And then we would wander off in whatever direction we were going last. But there would be that 8.5 minute lag, because that's how long it takes for light to get from the sun to the Earth. Now, how that corresponds to what we're doing here is, remember that heavy object that was in the middle of our elastic sheet? Now take it and wiggle it back and forth. So when you pull it one way, space curves down underneath it. And when you move it back the other way, it snaps back into place. And that up and down change of curvature ripples outward, as if you threw a rock into a pool of water. So that's a two-dimensional picture. Three-dimensionally, when you warp space like that, what you are doing is you're actually changing the distances between objects. So if somewhere out in space, a black hole is orbiting some other object and making these little ripples in the curvature of space, eventually they pass through us, and the distances between you and I are doing this. And we'll talk about by how much in a minute. But here's the thing. All of this is predicted by Einstein's theory of general relativity. Sort of. Here's what I mean by that. Imagine you took 2 neutron stars, 2 black holes, 2 enormously heavy objects that are wandering along through the universe, and they catch each other in their mutual gravitational pull, and they start orbiting around each other. Now, as they do that, they are radiating these changes in the curvature of space, which we're going to call gravitational waves. It takes energy to do that. Space doesn't like to curve, so you spend energy to make this change. That means these stars are going to lose energy and start to collapse towards each other. As they move closer to each other, they start to move faster, just like a figure skater when they pull their arms into their body when they're spinning. And as they move faster, they radiate energy even more quickly. So you have a system here that if you were to draw it as a wave, the pulses are getting more and more rapid, and they're getting larger and larger, until by the time a typical pair of neutron stars or black holes crash into each other, they would be orbiting each other a few hundred times per second. I never feel like that number gets the respect it deserves. I just told you 2 stars are orbiting each other a few hundred times per second. That should be the most shocking thing you hear all day. But anyway, another thing about that frequency is that's an audible frequency. So you could imagine I could play that through an audio speaker and I could hear it. It's getting higher in frequency, which is pitch, and it's getting higher in amplitude, which is volume. So let's see if I can do this without blowing out the microphone. The sound it makes is like this. And then they hit each other. So we call that a chirp, because if I had a higher voice, it would sound very chirp-like. So then the 2 objects crash into each other. And then something happens. Now here is the crazy part. General relativity tells us exactly what happens when these objects hit each other. The problem is we can never, ever solve it, because general relativity is a matrix, a 4x4 grid of 16 differential equations, the solution to each of which depends on the solution to the other 15. So what do you solve first? You can't. All you can do is pick some starting values, take a small step forward in time, and resolve all the equations using the values from one time step ago. If your time step is too big, then that assumption is terrible and you diverge from reality over time. If your time step is too small, great, you have a good prediction, and all the supercomputers in the world will never finish. And there's really nothing in between. So we have a complete theory, general relativity, of how black holes, neutron stars, all these crazy objects should behave. And it is useless to us because we can never solve it. All you can do is make kind of gross assumptions, and when you do, what you find is eventually these 2 colliding objects should slowly settle down into one pulsating bigger object, and you get what we call a ring down, which is kind of the chirp backwards. But here's the thing. If somehow you could directly measure these objects, and you saw the chirp, and then you saw some stuff, and then you saw the ring down, everything in between was the information that general relativity would not give you. So the idea here is if somehow you could measure these changes in the curvature of space-time, you could study objects that we cannot study in any other way, because the math is just not solvable. So that's the goal. We're trying to look at super heavy objects that we can't look at in any other way. Now, I talk about all this as if we're absolutely certain these things exist. And that's because we are absolutely certain that these things exist. The reason is kind of clever. There were a couple of astronomers from the University of Massachusetts Amherst named Halson Taylor who were cataloging pulsars. Their entire job was they were looking for, finding, and very carefully recording all the different stars they could find that were giving off regular pulses of X-rays over time, of which there are many. And they found a particular one that was pulsing 17 times per second, except once every 8 hours, it stopped. And then about a minute later, it would start again. Now, there is no reason any star should do that. So what they finally decided was it was actually pulsing the whole time. It's just it had a dark, invisible brown dwarf partner orbiting around it in the plane of our eyesight. So once every 8 hours, it would get in the way. And it would block the pulses and then move aside. Okay, 2 things orbiting each other. That's a system that should give off gravitational waves. That should make them lose energy. That should make them fall towards each other and spin faster. So they calculated how much should that 8-hour period drop because of them spinning around each other more quickly because of losing energy to gravitational waves. And what they calculated was it should drop by 10 seconds. So from 8 hours to 7 hours, 59 minutes, 50 seconds in 20 years. So they measured it for 20 years. Again, never feel like that gets the respect it deserves. The axis on this graph, this is year. There's 1975, there's 1993. This is how many seconds less than 8 hours the period is. So it starts at 0 and it drops and it's 14 seconds shorter by there. Whenever I show this, the usual reaction is, oh, the line or the curve fits those data points very well. They drew that curve in 1975. They took that data point 17 years later, and it hits the bullseye right on there. This is why we're sure gravitational waves exist. They never actually saw one, but the indirect proof that all the energy loss is precisely due to those things is just overwhelming. So, now, have any of you seen this picture? There was a big sensation about 6 months ago about an experiment called BICEP-2. And if you saw today's talk with gravitational waves, you might have remembered this. There was an experiment that claimed to have found that there was gravitational radiation produced during the Big Bang and the inflation period that occurred after it. And long story short, the way they did it was there's something called the cosmic microwave background. It's infrared light from the early creation of the universe. And all that light is made up of waves, and all the waves are radiating in some direction. And all these lines represent the direction in which the light is waving. And you would expect them to all look like starburst patterns radiating out from a point. But if there was also gravitational waves produced in the early Big Bang, then that will warp the space in between the light and us. And as the light goes through it, it will bend. And instead of starburst patterns, you'll get kind of twisted spiral patterns. And you see that all over the place, right? Especially right here, these vortices forming here where there's spiraling. And so they announced that they had found evidence of gravitational waves. Unfortunately, that's not the only thing that can do that. It turns out, believe it or not, another thing that can do that is dust. Now, they knew that, and they had gone to another experiment to figure out how much dust was in the way, but that experiment wasn't done, so they used a preliminary number, which said there wasn't nearly enough dust to do it. And then it turned out that that number was wrong, and there's way more dust than they thought, and so now they're not sure of their result anymore. I bring this up for a couple reasons. One, that doesn't prove or disprove the existence of gravitational waves. It just means what they saw could have been caused by that, could have been caused by something else. It's really kind of it's a shrug at this point. They don't really know what they have. The second thing is, even if they found them, that's still not quite so interesting, because ultimately, remember, what we want to see is the shape of the wave itself, not just that it exists. So we can do astronomy with it. But the third thing is, this is how science works. I see this reported in the media now as, oh, crazy science people have been shown to be lying. No, they had a result. Further clarification, it turned out that result was slightly wrong. And do they cover it up? Was there an investigation? Were people jailed? No. This is how science works. They wrote a paper that's 6 months later that said, you know what? Turns out there was more dust than we thought. My bad. That's how science goes. All right. There's more things, by the way, than neutron stars and black holes. Supernovae, that's a lot of mass moving very quickly. The fun thing about supernovae is the gravitational waves that are produced when a star explodes just shoot right out and come straight toward us. The light does not, because the explosion starts in the center of the star. There's a lot of stuff in a star, and the light scatters around for hours before it escapes the outer envelope. So if you could detect gravitational waves and you could triangulate where they came from, and it looks like the burst that you would expect from a supernova, you could call up the Hubble Space Telescope and say, look there, and wait 4 hours. And then you'll catch, because usually how do we catch supernovae right now? Some farmer looks up and says, that star didn't used to be there. And they call someone, and now it's too late. We're already 12 hours in. We don't really catch supernovae from the moment they begin, but now we could. Dark matter, dark energy, what does it look like? I don't know, it's dark, right? These are not things we've ever seen. They are things we know the existence of because of their effect on the matter around them, but now you can look directly at their gravitational effects. And of course, the most exciting thing is every time you make a new telescope of some kind, you discover an object you didn't know was there before. That's happened when we got radio waves, X-rays, infrared. Every time something new comes up. So of course, there's the hope that that happens with gravitation too. So enough dissembling. How big are these waves? It turns out the effect is a change in length per unit length. So if I measure a 1 meter distance, it'll change by a certain amount. If I measure 2 meters, it'll change by twice that much. So we call this a strain. I take the change in length per unit length. That's the number that tells me how big it is. So what I'm going to do is I'm going to take two neutron stars. Each has roughly the mass of our sun. But these are old stars that have burnt out their fuel, collapsed, and only the mutual repulsion of the nuclei of its atoms are keeping it from plunging all the way down to a black hole. So each of these stars has the mass of our sun, but roughly the size of the 410 freeway. Really not getting the respect I deserve. We've just become so, I could say anything. And then they talk to each other and nothing, no reaction. All right. Now, and so they're about to collide with each other. So they're roughly 20 kilometers apart. They're orbiting several hundred times per second. Jaws to floor, thank you. And this would be bad if it were in our galaxy. This is not the type of cataclysmic event we want happening next door. So let's say it's in the next big cluster of galaxies over, which is called the Virgo supercluster, which is about 60 million light years away. So huge cataclysmic event, as close as I'm willing to contemplate. How big of an effect does this make? And it turns out to be 1 part in 1 followed by 21 zeros. And it's okay if you don't react to that because that's a meaningless number, right? What is 21 zeros? So the best analogy I could come up with is that the distance from the Earth to the Sun is about 10 to the 11th meters. The width of an atom is 10 to the minus 10. So what we're looking for is an event that will change the distance between the Earth and the Sun back and forth by the width of an atom. At most, that was a huge event, right? Most of them will be smaller than that. So that could be rough. So the next question is then, why don't we generate our own? So what I'm going to do is I'm going to make a barbell. I'm going to put a 1-ton weight on either end. It's just going to be a 2 meters, basically 1 meter in radius. So about person length long, 1 ton at either end. And I'm going to spin it so it spins a few hundred times a second. Already, I have created an object that can never exist on Earth. It would just rip itself apart from the stresses of curving that quickly. But let's pretend I could. And rather than have it be 20 million light years away, or 60 million light years away, I'm going to put it right on top. Basically, my detector's on the floor, I'm holding it here, and I spin it. How big is that gravitational wave? And it turns out to be 1 million billion times smaller. There's no way you can generate these things on Earth. You need mass, lots of mass. And you need planet-sized masses. You would have to spin the Earth that fast, which would be dangerous. So we have to measure these tiny things coming from the cosmos. So how are we going to do that? So we build an interferometer. That's it's so called because it interferes things together. In this case, 2 waves of light. You take a laser and you split it so that half the light bounces off and half the light transmits through. You have them go some distance, come back, and when the 2 beams recombine, light is a wave. And depending on how far one wave traveled compared to the other, they might still be in phase, or they both crest and trough at the same time, in which case they add together and you get lots of light. Or they might be out of phase, where one crests as the other troughs and vice versa. And then they cancel each other out and you get no light, or anywhere in between. But the difference between these 2 situations is only half the wavelength of light, which for a typical red laser is only about, like this thing, is only about 300 nanometers, or 1,000th of the width of a hair. Even that's not good enough. 2 improvements you have to make on top of that. 1, again, it was a change in length per unit length, so you need as much length as you can. So you make these arms as long as humanly possible, which turns out to be about 2.5 miles, before the Earth curves out from under you, and it's hard to build it straight anymore. So that's not good enough. So then, instead of just the light going down and back, it actually bounces back and forth between 2 mirrors several hundred times. So by the time the light recombines, it's traveled about 1,200 miles or so. And then it's not good enough to tell the difference between light and dark. You have to tell the difference between light and dark to 1 part in 10 billion. And if you can get there, then you have enough sensitivity to measure that event I described earlier. So we totally built that. It's called, again, LIGO, Laser Interferometer Gravitational Wave Observatory, because LIGO doesn't sound as good. And again, this is not a project that is ultimately designed to detect a gravitational wave, throw a party, and then pack it in. Ultimately, this is intended to be an observatory, a long-running program, just like the Hubble Space Telescope, that's going to be there for many years to do astronomy on objects we can't detect in any other way. It's actually a group of over 900 people, dozens of institutions, mainly Caltech and MIT. Again, I started at Caltech and then kind of brought it here. And it's entirely funded by the US National Science Foundation. I did not make this slide. This is the slide that the collaboration supplies to people when they give outreach talks. And I point that out because I think it's pretty cool that we're the absolute first thing on the logo. I didn't make that slide. So that worked out nice. If you want to see where Texas is on here, by the way, they're here, and then UT Brownsville, which will soon be UT Rio Grande Valley. And that's it. Texas Tech will be in there eventually, because someone just moved there. But right now, those are the only places in Texas that are involved. But the other thing is, you can see there's a lot of international representation. We have Korea, let's see, United Kingdom, Australia, China, Louisiana, and so on and on. So here are the observatories. Again, that's 4 kilometers long, which is about 2.4 miles. It's just like the thing I showed you. The laser is in here, the splitter is in here, but then the light travels all the way down and all the way back, here and here. That is in Washington State, what's called the Hanford Nuclear Reservation. It's a very empty area where the US tests all of its prototype nuclear reactors of the future. So it's very barren. It's perfect. They've also got kind of an Area 51-ish relationship with the surrounding locals. Remind me at the end of the talk to come back and tell you about the crazy person on the airplane. It's the best story ever. But we'll save it for the end. You can tell Livingston because it's sinking. This is Livingston, Louisiana. That's water. The other problem is they're logging that forest. So every 20 years they come in, they cut all the trees down, and they replant them. They're just about done, fortunately. But for a few years, it made running very difficult. Everything about this instrument is a superlative. It is the largest vacuum system in the world. That pipe is about 4 feet in diameter, and again, between the 2 arms of the L, it's about 5 miles long. The vacuum in it is so good that it maintains about a 10 billionth of atmospheric pressure, even with the pumps off. And when you turn the pumps on, it drops to about a trillionth of atmospheric pressure. All of which is necessary because if there's any air in there, it will scatter the light away from having to bounce back and forth so many times. To give you a sense of scale, so the beam would be right about here. That is precisely eye level for me. The beam, by the way, is also invisible because it's infrared, and it is sufficiently strong that it would basically blind you instantaneously if it hit you in the retina. So again, we have an invisible instant blindness laser that is precisely at my eye level. It is a wonderful place to work. But no, we have safety glasses. There's all kinds of interlocks where the laser can't be on when people are working inside. But that gives you a sense of the size of these chambers where all the optics are kept. Is I'm that tall. So, okay. Everything is kept very still by using what we call passive seismic isolation. When you have any kind of harmonic oscillator, a pendulum, a spring, anything that oscillates back and forth, there's a particular resonance frequency where it likes to oscillate. If you shake it at a frequency higher than that, it doesn't move as much. Because every time it starts to move one direction, you're already pulling it back the other. And the motion gets smaller by 1 over the frequency squared for every oscillator. So we stick in as many oscillators as we can. There's springs, more springs. Hey, how about some more springs? And then the optic itself is suspended from a pendulum, which is yet more oscillators. Even that turns out to not be enough when they're cutting the trees down. So there's an amazing thing in here. It is a crystal that's called a piezoelectric crystal that expands or contracts when you apply an electric voltage to it. And so we put these under the supports that hold the 2.5-ton optical table in place in each chamber. And there are seismometers sensing the motion of the ground. And if the ground shifts, then it sends an inverse signal to the crystal to expand or contract and move the 2.5-ton table up or down to precisely compensate for the ground motion. And with that, we can use the laboratory even when they're cutting trees down. I always think this picture is a little unfair because she's extremely short. She's about 5 feet tall, so it makes the mirrors look even bigger than they are, but they are quite big. The bigger they are, the less their thermal vibration matters. And again, they are hanging from pendula. And this is from the original version of the instrument. This picture is from about 2005. So this horrifying graph is how we express how sensitive the instrument is. This right here is the strain that it can detect. And remember that event I showed you was 10 to the minus 21. What's a little strange about this graph is this right here is the frequency of the wave we are looking for. So this is a gravitational wave that stretches things in and out 10 times per second, 100 times per second, 1,000, etc. And you see that there is a certain range of frequencies from about 30 per second up to several thousand per second, where we are sensitive enough to see these things. That's not enough to see stars when they're still orbiting each other, but it is the perfect range for when they just about crash into each other, which you remember was a few hundred hertz, right in the most sensitive range here, a few hundred times per second. Supernovae just kind of go, they go everywhere, so we can see some of that as well. The black line here was the ultimate goal of how sensitive to make the instrument, and it's limited by 3 things. Down here is all ground motion. In here is the vibrations of the atoms on the surfaces of the optics themselves just because they're getting hotter. That's how sensitive this is. Over here, you're limited by 2 things. One is how much the output of the laser is fluctuating from moment to moment, which the brighter the laser is, the less significant that becomes. The other thing is, over here, there are so many cycles per second. The gravitational wave is going back and forth so rapidly that it actually goes back and forth multiple times while the laser is still making its way down the arm and back. So it cancels itself out a little bit. So your sensitivity degrades. But who cares? There's nothing over here anyway. Or so we think. All the action should be here. Now you'll notice that all these different curves are improvements over time until in 2006 we finally got below the target sensitivity, which was great. So we ran with that for a couple years, from 2006 to 2008. And then there were small incremental improvements, tripling the laser power, different ways of positioning the mirrors. That got us down even a factor of 2 lower, and we ran that way for about an hour, for a year and a half. And so finally I get to tell you all the wonderful things that we detected during that time. And the answer is, Because here was the fun thing about LIGO. If you asked an astronomer before LIGO started to run, what is the expected event rate? How many gravitational waves should we see, say, per year? And depending on what astronomer you asked, the answer would have been 1 per year, plus or minus a factor of 1,000. Because that's how uncertain everyone is about how common these objects are. So we basically had a coin flip, and the coin came up tails. We didn't see anything. But that was always planned into the design, that with the technology available at the time that this was proposed, we would build a laboratory and we would see if we would get lucky. But while that was happening, a whole other host of people would be working on improvements to the technology, and that would go into place once this running had been complete. Now, even with not seeing anything, that puts interesting limits on things. For example, the Crab Nebula. It's an object that's very close by. It has a pulsar in the center of it. That pulsar is very close to us. We should be able to see it wobbling around its own axis, and we don't. What that tells us is that the pulsar, the sun-sized object, or originally before it collapsed, that is in the middle of the Crab Nebula has to be a perfect sphere to less than a meter. Otherwise, we would have seen it by now. Other interesting limits like that. But we're not interested in limits. We want to see things. We want to do astronomy. So while the original device was running, the rest of us were working on technological improvements that would make it see 10 times farther. Not 60 million light years. This time it's going to be 600 million light years. But it's even better than that, because this is not a telescope. It's an object that sits on the ground and receives information from all directions. So you're not looking in a particular direction. You are searching the volume of the sky at all times. So if you can see 10 times farther, then you will measure 10 times 10 times 10 more stuff, or a factor of 1,000. So even that most pessimistic person who said you would see 1,000th of an event per day now has to say, or one per year, has to say, you should get about one per year. And on average, it should be more like 20 to 40 per year of neutron stars and black holes crashing into each other, somewhere within our range. So lots of technological improvements went into this. The laser power is now all the way up to 200 watts, which, if you think a typical light bulb is 30 to 60 watts, imagine the heat from 3 to 5 of those light bulbs concentrated into the thickness of a pencil lead. Right? That's a tremendous amount of power. Now imagine that power is bouncing back and forth several hundred times in those arm cavities, so where it's all adding together. By the time you're done adding all this up, there is 650 kilowatts of laser power stored in the arms at all time, the 2.5-mile long arms. An amazing thing was done with the optics. The way you can't cool them down, because they're in a vacuum. There's no way you can cool something in a vacuum. So they get hot, but what you do is you get a material that rings like a bell, that only wants to vibrate at very particular frequencies. And then all the thermal vibration goes into that particular frequency and nowhere else. And so you just ignore that frequency and you measure everywhere else. The problem is then you have to position that optic in a very precise place. So you have to stick positioning magnets on it. And that's like sticking chewing gum on a bell. Right? Now it sounds like thud, and all that thermal vibration goes into a bunch of different frequencies. People actually found a way to chemically fuse ribbons of glass from one piece of glass to another piece of glass to create a second pendulum. So you put all your positioning magnets up here, but the light actually hits this optic down here, which, as far as it's concerned, it's just a piece of glass. And so it rings perfectly like a bell, and all the thermal noise drops away. Of course, that causes all kinds of other problems. Now you're trying to position this by moving this. There's a lag between the two. It's a frequency-dependent lag. It's a horrendous controls problem. So that's actually what I work on, is this thing right here is an electrode pattern that sits behind the optic that has a huge voltage on it that attracts the little bit of electric dipole that's in the glass molecules and pulls them. And so by adjusting the voltage, you can adjust the position of the glass. And that causes all kinds of other problems. First of all, it's not proportional to the voltage. It's proportional to the voltage squared, because nothing can be easy in life. And then second, it has to be so close that it ends up actually rearranging the charge on the surface of the optic, and then that charge has such strong self-repulsion that even though glass is an insulator, eventually it overcomes that and starts conducting across the surface, and that creates an electric field which vibrates it and ruins everything. So I'm one of 900 people, but with my little lab up on the 3rd floor, I work on how quickly does the charge build up, what materials inhibit the buildup of that charge, how can you get rid of it once it's there. And then just me and my 1 or 2 undergraduates at a time, whatever we find gets sent up to the full-size observatories. So, again, there's 10 to the minus 21. We just turned on June 1st, 2014. This is the Louisiana one. It's finally been built. Within 2 months, by the end of July, it was already below the sensitivity of the original LIGO instrument. And now, as of 3 weeks ago, it's down here, a factor of 2 better. We've only got about a factor of 3 to go. Also, a very exciting thing, we're not the only game in town. These are our 2. There have always been one in Germany, one in near Pisa, Italy. We actually share data with this one, so they might as well be a companion instrument. One in Japan, that got held up a little bit after Fukushima, but it's starting to rev up again. But the very exciting recent thing is funding has been established to build a new partner interferometer in India just recently, and they should be done in a few years. But it's nice for triangulating where things come from to have multiple instruments in very far apart places. So the ultimate goal here is, I mean, we're already running. The hope is to be within a factor of 2 of the design sensitivity within a year, to be fully up and running within 2 years, and then eventually, when the India interferometer comes online, to be doing even better than that. So I've been giving these talks since I joined the collaboration in 1999, and I always have to put up that not so much slide. I've been doing that for 16 years. I'm telling you right now, we're 2 years away. If I can't come back in 2 years and say we saw something, technically that's almost more exciting. Right? The Higgs boson people found the Higgs boson exactly where they thought it would be. Huh, now what, right? Here, both options are great. If we see gravitational waves, we can start doing astronomy. If we don't see it, general relativity is wrong. And then what do? Right? That's kind of exciting too. So, anyway, I always like to finish with, would you like to learn more type thing. So a couple of good books that are written for the non-technical, non-math person. Black Holes and Time Warps by Kip Thorne, who's one of the original kind of theoretical side of general relativity and what gravitational wave patterns should look like. He was also science advisor for the movie Interstellar, although I don't think that was the most positive experience for him. Certain things he really wanted in the movie, didn't quite get into it. But anyway, this is a fantastic book. And then this, Marcia Bartusiak, is a science journalist. And this is all about the history of the entire field back to the early 1970s, long before LIGO even comes into fruition. There's a website which has all kinds of things for just the generally interested and also teacher materials. And we have a magazine which has ridiculously nice photography in it, and 6 issues going back to 2012. And you can find it at ligo.org/magazine. Thanks for having me today. I hope you enjoyed it. Questions?
Isn't there another facility in Minnesota somewhere underground?
There is a facility called Sudan, which is an old mine in Minnesota. That's for neutrinos and not for gravitational waves. They are partner institutions in the sense that, remember I was talking about supernovae and the gravitational waves shoot right out? Neutrinos also shoot right out. So neutrino observatories and gravitational waves observatories cooperate in what we call the supernova early warning system, that if they both see an event that they can triangulate back to the same place, the idea is to transmit that to visual telescopes in the future. Yeah.
I don't think you told us about the funny story of the airplane.
Oh, thank you. All right, I'll make this quick, but it's the most amazing story. Again, I've been in this collaboration since 1999. And when I first joined, I had to fly out to that. Now again, it's in the middle of absolute nowhere. It's what's called the Tri-Cities, Pasco, Richland, Kennewick. 3 small places, about 100,000 people total. My first introduction to this place was I went to see a movie one night while I was there. And they had a preview for the movie Signs. You remember that with Mel Gibson about the crop circles? And the trailer started by showing all these real-world crop circles that had cropped up in different places and where and when. And one of them popped up and it said 1985, Kennewick, Washington. And that's where I was. And everyone in the theater went, yay! So, and again, they have this very Area 51 relationship with the nuclear reservation part of things. They know there are nuclear engineers there. They know that's where they go off to work. They don't really know what happens when they get there. The only publicly accessible part of the whole 400 square mile area is the LIGO Observatory. Everywhere else, there's big Marines with machine guns who turn you around. So you can't fly directly there. You fly into Salt Lake City or Portland or Seattle, and then you take this tiny little propeller plane, 1 seat on each side. And that's what I was. I was in the back row, and there was a local woman, and all I had told her was that I was coming in to apply for a job, and then she talked the whole rest of the flight. So she doesn't know why I'm coming. This is 1999. They've just finished building this. As I'm flying in, and we pass over it, and you can trivially see it from the air because it's 4 kilometers long. All of a sudden, she gets very quiet. And she leans over to me very conspiratorially and she says, "You see that? They won't tell us what that is, but we know the truth." I said, as I'm quickly closing my bag that has pictures of it in it, I said, "Really, what is it?" She leans in even closer. She says, "It's a time machine. They put you in the middle, and they launch you down to the end, and by the time you're going, at the end, you're going fast enough to go back in time." And I said, "That's fascinating, but why is it an L? Why wouldn't it just be a straight line?" I swear to you, she does this. "They have to come back." Best conspiracy theory ever. I love it.
Is the practice piece that you have on the third floor, is that to scale for the actual
So,
glass in the...
No, I have a vacuum system that's about a little bigger than shoebox size, and it has one optic, what's called a witness sample. It's only 3 inches in diameter, but it's to test the materials and the coatings in an otherwise LIGO-like environment. The vacuum is similar. There's an electrode pattern right above it that's similar to the one you saw there. But since all I'm doing is measuring effects on the glass and not actual gravitational waves, it doesn't have to be big, right? It just has to have room to put a material in it. So there's a long remote control track where it slides the optic under the electrode pattern, exposes it for a while, then slides it to the other end of the chamber where there's a little charge-sensitive probe that then makes a map. And the whole thing has been automated by undergraduates, because never underestimate an undergraduate's ability to get something else to do its work for it. Because originally I said, go in there and measure this every 2 hours. No. And within a day, they had code written that automated the entire process, and off they went. So, which is now great for me, because I just hit a button and I'm taking data right now. I'll repeat. I'll repeat your question. Go ahead.
I am a layman's layman, and I'm going to ask what might be a dumb question, but Steve Jobs said he was about changing the world. That's what he thought every day when he got up. Can you speculate on how what you're doing is going to change the world in a sense that a layman can recognize?
Okay, so the question is, what is going to be world-changing about this experiment that a layman would appreciate? So I have 2 answers to that. The stock answer and then my answer. So the stock answer is the astronomy of this gets to the creation of the universe, the Big Bang, the evolution of the universe over time, the types of objects that we see. It is wrapped up with cosmology, and if our reach does not exceed our grasp, then what's a heaven for and all that. All right, that's not my answer. I am a pure experimentalist. I am an engineering electronics junkie. I'm pretty much half physicist, half engineer. I'm on this project for one reason, and that's that every technology in here basically had to be invented for this purpose. There is so much. It is, again, the largest vacuum system in the world. Those optics are the most reflective optics in the world. There are n different blah, blah, blah in the world that I could give you about this system, because all had to be created or it never could have reached this level of sensitivity. So for me, basic science is always about, you do the basic science because the results are interesting and we should be inquisitive, because what else are we here for? But also, there's all these technological spillovers that come out of it that then find their way into any number of other industries and applications.
Washington State is one of the most seismically active areas in the United States, and there's many very small earthquakes that happen a lot, and I know you were talking about how that's compensated for, but doesn't that make it difficult? Isn't that a difficult location for locating the observatory?
So it turns out it's actually better for the most part, and the reason is this. Washington is about 10 times more seismically active than Louisiana. And here, for that matter. But right now, whether you realize it or not, you are all shifting back and forth at about once every 6 seconds by about a micron either way. Do you know why? When do you move like this? Not so much here, more so in California. Right. Tidal motion, right? The Earth, everywhere on the Earth, is experiencing tidal motion. It's just more obvious in water because water can move. Right? But the ground is experiencing tidal motion too. You're vibrating back and forth right now. So is Hanford. Hanford vibrates back and forth by about 10 microns. We vibrate back and forth by about 1. Both are well within the compensation range of the active and passive seismic isolation. Hanford has the occasional tremor. Livingston has the occasional train. They actually kind of even out. They jiggle things, and you wait, and then they eventually settle down. An earthquake above 6.0 on the Richter scale anywhere on Earth will knock both interferometers out of alignment. And it's fun to watch when you're in the control room because we have, very much like the one in geosciences in Mars-McLean, the big map on the board from the US Geological Survey showing all the earthquakes. And it'll pop up and say 6.2 earthquake in Kamchatka. And you can set your watch by it. If 40 seconds go by, Livingston knocks out, wait another couple minutes, and Hanford's gone. Right? And then it takes a few minutes, and then it settles down, and it comes back into play. The only problem was there was one day when there was a huge earthquake in Hanford, or in Washington State, that was over 6.0, and it sufficiently wobbled one of the mirrors that it diverted the laser such that it cut through the suspension wire of another optic and severed it like a samurai sword. It's just think, boom. But we have little bolts with pads on them that are there to catch the optic for just that very situation. So one magnet got snapped off, I think, 1 or 2. So they had to take it out, re-glue it, re-hang it, pump back down. I mean, that took several weeks. I don't want to downplay it too much, but it's not like it destroyed the optic or anything. So for the most part, the seismic noise cancels out because we really are all experiencing seismic noise for one reason or another, because of tidal motion, because of people motion, but it's all removable at the frequencies we care about.